Hello everyone. Good evening to one and all present here. This is going to be the fifth weekly live session for the NPTEL course of Remote Sensing Principles and Applications. I am Abhishek Chakraborty, a PhD student under the Prime Minister's Research Fellowship Scheme in the Interdisciplinary Center for Water Research (IISc) at IISc Bangalore, and this course is being tutored by Professor Ishwar Rajshekharan from the Department of Civil Engineering at IIT Bombay. So let me just start with the common instructions and informations which I always share before starting any weekly live session. The first one is that the video recording of the sessions will be made available on the YouTube channel. I've already shared the link, so I always make sure to upload the video recordings on the very same day of conducting the weekly live sessions. Secondly, the files relevant to the sessions will be made available through a Google Drive folder. So far, I've already uploaded all the files till the last lecture, a weekly live session on that Google Drive folder. The link has also been shared with you already. Thirdly, the files and the video recordings will be made immediately available after the class. I will try my best to upload it within an hour after the class weekly live session ends. Okay, someone is trying to enter. And the fourth of all, the images, if they are taken from the internet, are solely for study purpose. We don't intend to use copyrighted content, but it is only for educational purpose mostly. So far I've already uploaded all the first four weekly live sessions of this NPTEL course conducted by me on this YouTube channel, and the spreadsheet here, the link for the spreadsheet here would actually contain all the files which I've actually uploaded with the illustrations of the weekly live sessions, as well as the links for the YouTube videos. You might already have all the links with you. So today's weekly live session is going to be a bit different. We will firstly start with a few uh, uh, questions, and then we will move to some practical examples. I will illustrate the usage of remote sensing based approaches through some MATLAB coding based approaches. However, I mean, as you know, these approaches can be connected on any other software also, or any other programming language also. You are also free to use interfaces like R or Python to do the same. Yeah, so we will firstly start with some common questions for the day, and then we will move. So the first one is that for still water, the reflection from water surface will most likely be dash at the visible and NIR wavelengths. So what happens is that this question uh, depends a lot on the roughness features of the surface. Different surfaces, may have different roughness. For example, let us say a soil. Let us say a surface which is soil. It may have very different surface from, let us say, something like a polished metal, or even a mirror, or even, let us say, still water. So it depends a lot on the surface features. The correct answer is actually specular reflection. B is the correct answer, but I will explain in details how we actually arrived at it. So the reflection from any surface depends on the roughness characteristics of the surface, that we know very well. So the thing is that uh, if the surface is smooth and shiny, for example, let us say glass, or water when it is still, okay, or polished metal, the light will reflect at the same angle as it hit the surface. So that is the basic thing. Now, what would happen if the surface? I mean, the first explanation was the one in which the surface was smooth. What would happen if the surface, I mean, was rough? For a rough surface,
सर रफ होगा तो
हाँ
स्कैटर
बोलिए।
हो जाएगी,
क्या हो जाएगा? सॉरी।
स्कैटरिंग होगी।
Yeah, correct, correct. So it would be
रफ है।
more. You're correct. You're correct. डिफ्यूज रिफ्लेक्शन होगा, ठीक है। अगर रफ होगा तो आई विल स्टिल, मतलब वी आर डिस्कसिंग इट हेयर, बट आई स्टिल इंटेंड टू राइट इट डाउन सो दैट यू कैन कंसल्ट इट इन फ्यूचर। आई मीन वेन एवर यू आर प्रिपेयरिंग फॉर एग्जाम्स और इवन आई मीन for some interviews related to remote sensing. So that is why I intend to, I mean, write it down also. And but you are correct actually. If it is a rough surface, then it would be a diffused reflection, and I will explain how they are different. For a rough surface, reflected light rays scatter in all directions. This is called diffuse reflection. So that scattering is actually known as a diffuse reflection. There is a terminology for that. Let me take another slide just to explain it using a diagram. You also, I mean, you also read about it when you were studying about the Lambertian surfaces. So this is not a new concept to, I mean, to this course as of now. So it's a completely smooth surface. So this is something known as the specular reflection. And it happens mostly when the surface is smooth. Now, what would happen if the surface is corrugated or rough? Let us say this is the surface in this next illustration. So here we see that the light rays which were parallel incoming, they will not be parallel when they will be outgoing, because it will depend on the normal to the surface on which the light rays are hitting. So this is something known as the diffuse reflection. So water body, the question was about the water bodies. Okay. So water body with waves would have roughness. But this question is effectively about still water, not wavy water. So okay, so water body with waves will have roughness, and so may not be specular. But still water is predominantly specular. It exhibits predominantly a specular kind of reflection. Still water. So that's the storyline. Uh, so that is what this question actually wanted to ask you. Uh, any idea what happened in? I mean, can you recall what kind of reflection happened in a Lambertian surface? You can feel free to unmute yourself. Just trying to admit. Any idea about the Lambertian surface? So Lambertian surface also showed a bit of a diffuse reflection, but it was a very idealistic condition. So that was a difference. Uh, Now let's move to the next question. Uh, the index NDSI is used A to identify the soil type in an area, B studying the soil moisture content, C to identify the presence of snow, or D to identify the salinity of soil. So, any idea? I mean, what is NDSI exactly? NDSI full form is normalized difference snow index. So, what would be the correct option?
Third.
Yeah, you are correct. As the name suggests, the name itself has snow. So it is about normalized difference snow index, and it is to identify whether the snow is present in a pixel or not. But I will explain it in a bit more detail. Difference snow index. So this is used to detect or identify the presence of snow, to detect the presence of snow in a pixel. Okay, so I have added these two figures, and these two figures are added for a certain reason, where I will come to it a bit later. The first important thing about snow is that snow, I mean, if you notice its uh, reflectance feature, spectral reflectance feature, it has very high visible reflectance. So for snow, I mean, if you move to this figure on the top right of yours, the reflectance is almost touching 100 percentage in the visible range, and very low reflectance in shortwave infrared region, SWIR. Okay, so this is the shortwave infrared region, 1.55 to 1.75 micron. So this would be the region, and here it almost tends to zero. So from around 100 percentage, the reflectance drops down to almost zero in the shortwave infrared region. This is what this band is also showing in the diagram which is right below it. Himawari 8 is actually a satellite. So I mean the name. This is a satellite basically. Okay, so it suddenly falls down. Okay, so very high visible reflectance and very low reflectance in the SWIR. So we need to, I mean, scientists at that time, I mean, when they wanted to detect snow pixels through satellite remote sensing, they wanted to devise a particular kind of an index to understand it, just like the NDVI, which is the normalized difference vegetation index. Okay, so let's see. And this was also to detect NDSI was also built to detect snow by distinguishing between snow and cloud surfaces. Now you see here, move to the topmost diagram, or even this diagram, both the diagrams, you can see that in the visible range, the reflectance magnitudes of snow as well as cloud, they're very similar, by the way. They're almost equal to 1 or 100 percentage, whatever unit you want to speak about. So in the below figure, snow is in blue, and cloud is in orange. in the visible, and in the visible region, the reflectance is almost touching 1 for both these surface features. However, in the shortwave infrared region, the clouds still have a very high reflectance. You can see the reflectance here. The reflectance is nearly in excess of nearly point 0.7 for clouds, whereas for snow it is almost zero. So I mean, this actually index was actually devised so that we can distinguish uh, the snow as well as clouds, because they have very similar reflectance features in the visible range. So I will also explain what these how scientists actually devise this index. So NDSI, or normalized difference snow index, was devised very similar to that of the NDVI, the normalized difference vegetation index. The normalized difference vegetation index is nothing but the difference between the NIR band and the red band reflectances divided by the summation of the NIR band and the red band reflectances. We'll just write it here for reference. So this is the NDVI, and these things are the reflectances on the numerator and the denominator. On a similar way, NDSI was also devised. NDSI happens to be TM band 2 minus TM band 5 by TM band 2 plus TM band 5. And TM is basically the reflectance or the DNs from the Landsat thematic mapper. So it was present in Landsat 5 and 6 satellites, which I have explained in the, sorry, 4 and 5. The thematic mapper is actually the TM. So it had a very peculiar sensor known as a thematic mapper, TM. And this NDSI, when you want to calculate it through the thematic mapper, it would come out to be like this. So band 2 and band 5. Band 2 is, you can see, is 0.52 to 0.60 microns, and band 5 is a shortwave infrared band, which is 1.55 to 1.75 micron. So band 2 is visible green, which is 0.52 to, what was that, 0.52 to 0.60 microns. And band 5 is basically the shortwave infrared band, which is 1.55 to, what was the limit, 1.75 microns. Now let us say, so the numerator is basically the reflectance difference between band 2 and band 5. So numerator is, what would the sign of numerator be for snow? Any idea about it? So in the green band, as
Sorry
you
sir.
can, sorry, yes.
सर क्वेश्चन एक बार दोबारा पूछिए.
Okay, the question was that what would be the sign? I mean, whether it would be positive or negative on the numerator of this NDSI if it is a snow feature. I'm giving you a hint. The band 2 reflectance will be much higher than the band 5 reflectance. So the numerator will be positive, right?
पॉजिटिव.
Yeah, exactly. So there are a few suggestions from the scientific community. The suggestion is that a pixel with NDSI greater than 0 is considered to have some snow present in it, and NDSI, which is less than equal to 0, it is definitely a snow free land surface without any doubt, because the reflectance actually declines in the shortwave infrared band. Another thing, let's see what would be the NDSI for a cloud pixel. So for a cloud pixel, the band to reflectance will again be greater than the shortwave infrared reflectance band reflectance, right? So NDSI value, if it is very high, then it is certainly snow. If it is medium, it may be either cloud or snow. So that is the inference which I intend to give from this example. And if the NDSI is less than 0, then it is certainly a snow-free land pixel. Because snow always has the maximum reflectance concentrated in the visible bands. So we are done with this question. The correct answer was to identify the presence of snow. The third question is about the simple ratio index. So simple ratio index is the ratio of uh, A. NIR and red reflectance. B. NIR and green reflectance. C. SWIR and red reflectance. D. NIR and SWIR reflectance. So, any answer or any? I mean,
Yes. NIR and red reflectance.
yes, you're correct. That is correct. The answer is A. So, simple ratio index. Let me write it as SRI would be the reflectance from the NIR band divided by the reflectance from the red band. But let me just explain how it actually came to be. We know very well that the spectral reflectance feature of vegetation, it looks a bit like this. Or yeah, this figure already showed this. So there is a slight peak which happens in the green band. Just a second. Yeah, there is a first peak which happens in the green band, and that is why you see the vegetation to be green in color. Then it dips again in the red band, which is something known as the red edge, and then again shoots up in the near infrared region. The peak reflectance actually happens in the near infrared region, but our eyes certainly cannot detect colors beyond the visible range. So there is a way to do that also. I will explain it in the later part. Anyways, and then then it declines after that beyond near infrared range. Okay. Now there are a few dips in the visible range. These are basically because of chlorophyll absorption bands. Then there are three prominent dips. First one happens at 1.4 micron, 1.7 micron, and 2.7 micron. These happen because of water absorption, which is present in the leaf, and due to that, the water absorption band feature happens. So that is the funda behind it. 1.4, 1.9, and 2.7 microns. At these wavelengths, there would be a dip in almost all the features. You can see that even the soil spectral reflectance is showing a dip in 1.4 micron, in 1.9 micron, and it will again show a dip in when you move towards the 2.7 micron wavelength. That is because anything which contains water will show some sort of water absorption in those wavelengths, which is something known as technically known as the water absorption band. Okay. Now, the simple ratio index (SRI) was defined as the reflectance in the NIR band to the reflectance in the red band. And why was it devised? Was because the reflectance in the NIR band, as you can see, it is actually much larger than the reflectance in the red band. The red band reflectance is very low, whereas the NIR band reflectance is very high for vegetation. On a relative terms, I'm speaking. So the simplest way to detect whether the pixel has vegetation or not would be to just have a ratio of the NIR band to that of the red band. If the ratio is too high, that would mean that there is a presence of a vegetation. Also, if there are two different types of vegetation, and if there is a change in the ratio, then ideally a higher ratio would indicate that the vegetation is healthy, and if the ratio is lower, the SRI ratio is lower, then that would mean that the vegetation is stressed. So this is the basic funda behind this. So this is the reflectance in the NIR band to the reflectance in the red band, or the reflectance at 850 nanometer to reflectance at 675 nanometer if you are using a spectroradiometer. This was the simplest vegetation index. However, we know that there are other vegetation indices also, like the Enhanced Vegetation Index or NDVI. So, the scientific community, slowly proceeded from VI to NDVI uh, and PRI also. I will explain them also in due course of time. This figure I pasted for another illustration, so I will keep it separately for the time being. Yeah, I will take another slide for explaining this. So the first vegetation index, which is actually the question is about the simple ratio index. So simple ratio index is basically the simplest vegetation index. So SRI is basically reflectance in the NIR band and reflectance in the R band, or around 850 nanometer to around 675 nanometer if you have a spectroradiometer. Okay, so green leaves, we know that they have very low reflectance in red and blue bands or blue regions. The peak happens at the first peak, but the lower peak happens in the green region. Leaves reflect more in the green region, and hence they appear green to us. Our human eyes can detect the light on a very narrow wavelength range, that is around zero point 0.4 micron to zero point 0.7 micron. So we can only see things within that range. So the first peak of reflectance actually happens at the green region for the leaves, and that is why we see it as green. But the most prominent peak, or the one which is much higher in magnitude, it happens in the near infrared region. Now talking about the magnitudes, SRI would be nearly equal to 1 for soil. Why? Because soil has high reflectance in both red and NIR bands. The reflectances are more or less similar also, okay, for soil. So that is why the simple ratio index will be nearly equal to 1 for soils. Whereas for vegetation, the simple ratio index would be much larger than 1 for green leaves. So, I mean, there is no doubt about it, because the reflectance in the NIR band is much larger than that of in the red band, and that is why the SRI is much
Sir,
larger than 1.
sir,
Yes.
इन 32 लेक्चर में सर ने ग्राफ दिखाया था सस्पेंडेड सेडिमेंट्स का, क्ले सॉइल का ग्राफ था। तो उसमें जो रिफ्लेक्टेंस है 700 पर, और 700 पर हाईएस्ट है,
Okay.
700 नैनोमीटर पर हाईएस्ट है, और इसके बाद वो डिक्रीज होती जा रही है। तो एनआईआर में कम हो जाएगी और रेड में ज़्यादा हो जाएगी।
सॉइल का, राइट?
यस सर, क्ले सॉइल 32 लेक्चर में सस्पेंडेड सेडिमेंट्स का टॉपिक पर।
ओके, तो यूजुअली हम लोग जो सॉइल इन सब टेक्स्ट बुक्स में लेते हैं वो है सैंडी, बेयर एंड ड्राई सॉइल। ओके, लेकिन अब अलग अलग सॉइल के फीचर्स के हिसाब से रिफ्लेक्टेंस विल वेरी।
सर इसमें सर नेगेटिव हो जाएगी
Yeah,
एनडीवीआई की
it can
वैल्यू।
happen. It can happen. So the magnitude which I showed would be for something like a bare, dry, sandy soil. Okay, so most textbooks, remote sensing textbook, they illustrate the spectral reflectance features for a bare, dry, sandy soil first, and then they move into the other cases. I mean, what happens if the water content in the soil increases? Will the reflectance increase or decrease? What happens if the orientation increases? What happens if the grain size increases or changes? So, I mean, that is how they take it. So, I am talking for a very generalized case for that of a soil which is bare, dry, and sandy soil. Let me also write it up. Bare, dry, sandy. Because this is the convention in all remote sensing textbooks. They start explaining about soil with the spectral reflectance features of bare, dry, and sandy soil itself. However, I agree with you completely. For different soil types, the spectral reflectance features will also vary. I'm not against that at all. Okay.
सर
Okay, so this was the simplest vegetation index. Simplest vegetation index. The second vegetation index, a bit more advancement on the SRI, was the normalized difference vegetation index. There are hundreds of vegetation index actually. You can I mean every single day scientists think of some new index and publish them also. So that is nothing wrong in that. But here I'm just going to explain the very basics. So the next one is NDVI. You know that it is basically the normalized difference vegetation index. NDVI is the reflectance in the NIR band minus the reflectance in the red band divided by the sum of these two reflectances. Or if you have a hyperspectral remote sensing feature, then 850 nanometer minus 675 nanometer by the sum of these two. And you know already that NDVI will vary between -1 to 1. I mean, there is no doubt with that. So, this is to monitor percentage of green cover in an area. And since, a very important point, since NDVI is a ratio, it is actually invariant to the difference in illumination conditions, slope, seasons, etc. Hence suitable for crop monitoring throughout the growth season. So we know already that if it's a vegetated pixel, if the pixel contains vegetation, the NDVI would be certainly greater than 0. There is no doubt about it. Now there is another vegetation index which I wanted to discuss about, and this vegetation index is in linkage with the terrestrial carbon cycle. I will take another slide, and this I mean, this figure was for that index itself, so I will just paste it in this slide first. Yeah. The third kind of index which I wanted to discuss about, there are hundreds of such indices, by the way. So, but the third one is photochemical reflectance index, or PRI. We can also build any new index depending on our own requirement. So it is a measure of.
सर पीआरआई एग्जाम के पर्पज से इम्पोर्टेंट है?
No, not for the exam. But I'm just trying to give an example, and this is actually very near to me because I do my research on carbon cycle itself. So I thought of discussing it. I mean, just to kind of what do we say? Introduce you to something new. Okay.
यस सर, थैंक यू सर.
Okay. So it is a measure of the light use efficiency of the foliage. So foliage actually means the leaves from the top, and thus and light use efficiency determines that out of a given amount of energy which is spent by the leaf, the chlorophyll, how much of the carbon from the atmosphere, that is carbon dioxide, it assimilates into its system, which is nothing but photosynthesis. Used primarily as an indicator of water stress and for the assessment of CO2 uptake by plants. So PRI is defined as rho at 570 nanometer minus rho at 531 nanometer by rho at 570 plus rho at 531. In many research papers, the numerator is actually even the opposite. In many research papers, they define PRI as rho at 531 minus rho at 570 also. So, I mean, whenever you're using photochemical reflectance index, make sure to look at its definition first. So it is something very arbitrary. Okay, anyways. So at this 531 range, if the plant is stressed, or if the plant is not able to assimilate carbon properly, then it will show a dip in the reflectance, as is shown in this figure. The yellow reflectance graph is that of a stressed one. So it shows a slight dip, whereas the green one is the one in which is normal. So the green one is the healthy vegetation. It has larger light use efficiency and hence larger assimilation capacity. And it happens because of something known as the carotenoid pigments, which are present in xanthophyll pigments inside the chlorophyll of the leaf. Okay. PRI in general will also vary from -1 to +1, just like the other NDVI which we discussed right now. For dark green, the dark green features here would mean that the productivity is high. Productivity means that how much amount of atmospheric carbon dioxide it is assimilating into its body. Higher it is, higher would be the productivity. and vice versa for the green, yellowish uh, plots. So that's it. Now let's move to the next question. The spectral reflectance of snow increases with increase in grain size. Did we? Yeah, we ticked that already. The spectral reflectance of snow increases with increase in grain size. State whether it's true or false. So, I mean, these kind of questions are a bit memory based. So scientists basically perform experiments, such experiments on labs, and then they detect the spectral reflectance features using an instrument known as a spectroradiometer. So it is in fact, I mean, it's a fact that with an increase in the grain size, the spectral reflectance actually does not increase, but it decreases. So its answer is false. So that's it. Let's move to the next question. As the depth of water column increases, reflectance emerging out of water decreases. State whether it's true or false. Decreases. Okay, depth is increasing. This is the water body, and this is another water body. It's a shallow water body. So, deep water body versus a shallow water body, and D is greater than D dash. So, what do you think? Whether the reflectance which will come out, which reflectance will be more? Whether it will be more from a shallow water body or from a deep water body? One hint I am ready to give is that the absorption percentage is very high from water bodies. So, any answer?
सर जिसमें जिसका डेप्थ ज़्यादा होगी तो उसमें रिफ्लेक्टेंस कम हो जाएगा।
करेक्ट, क्योंकि एब्जॉर्प्शन ज्यादा होगा, राइट?
यस सर।
हाँ, then you're correct. So it is actually true. The statement is true. Depth increases, that would mean that the reflectance decreases. I mean, it's a very easy question. Then moving to the next question. The NDVI may not properly indicate vegetation vigor in A. Low values of LAI, B. Mid values of LAI, or C. Large values of LAI. Anything you want to, I mean, answer? I mean, related to this. I'm giving you a hint. NDVI gets saturated at a particular range of LAI, by the way. Anything? Would you like to attempt this question? The NDVI may not properly indicate vegetation vigor in A. Low values of LAI, B. High values of mid values of LAI, and C. Large values of LAI. LAI we know is the leaf area index, and NDVI we already discussed is the normalized difference vegetation index. So leaf. Yes, 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 please. Yes, please, please feel free to comment. Yes, are you saying anything? Any comment from your side? Oh, I guess no comments. Okay, you may just unmute yourself and shoot your question straight away. I have no issues with that. Uh, so LAI is basically an index which gives you about the amount of leaves which are there in the entire biomass. So LAI is basically the projected leaf area, the leaf area to the ground area. So LAI is more, that would mean that there is a dense canopy. The canopy is very dense. And vice versa. If LAI is low, then the canopy is not dense. Anyways, so the relation between NDVI and LAI is like this. The unit of LAI is meter square per meter square. I mean, because it's basically nothing but a ratio of two different areas. So the after a particular LAI, the NDVI almost becomes saturated at large values of LAI, and that is why NDVI may not be properly, properly used when there is when the canopy is very dense. So the answer is actually C, large values of LAI. Now let's just wonder what might be the reason behind this NDVI saturation at high LAIs. So NDVI saturation is mainly caused by the reflectance contrast of the red and NAR bands. We know very well that there is a massive difference in the reflectance features between the red and NAR bands. So let me take another slide. NDVI versus LAI plot, it would always be like this: saturated at high LAI, that is for dense canopies, and there is a non-linear relationship overall. Non-linear relationship between NDVI and LAI overall. Now, what might be the solution? The scientific community, they knew that they had devised something like the NDVI already, and NDVI used to be a very good index, vegetation index, because it actually captured the difference between the NIR and the red band very properly. But they also observed that whenever the canopies became dense, the NDVI was not showing any difference. Okay, so they had to work on that, and then the scientific community built some more indices to counter this saturation issue. So let us see what these indices are. The so what would be the solution for this? The first solution was wide dynamic range vegetation index, or in short WDRVI. WDRVI was defined as A times the reflectance from NIR minus reflectance from red by the sum of these two same quantities. So it's very similar to NDVI, by the way. WDRVI is very similar to NDVI, but we have just added a coefficient A to it. And A is a weightage coefficient or weighting coefficient used to decrease the disparity in NIR and red band contributions. So this A coefficient should be ideally greater than 0 and less than 1. We basically penalize the contribution of NIR so that this saturation decreases a bit. Let me show it again. And why it happened was that because the red saturates red band saturates quickly, which resulted in the NDVI also saturating. So let me show that. If you plot the reflectance of red band to the reflectance of NIR band, you will see that the reflectance features will be like this. So after a particular NIR band reflectance value, the red band reflectance will almost saturate. It will not change at all, and that is why the NDVI also saturates. So a counter to it would be to penalize the contribution of NIR. That is what we did in WDRVI by adding this A, which is the weightage coefficient, to decrease the disparity between the two bands. So if you use this, yeah. So if you now find out the differences in the two vegetation indices. So let us suppose we plot the two vegetation indices. The first one, and with respect to LAI, which is meter square per meter square, NDVI would look like this. So after a particular value, it will become saturated, just like this. It's not changing at all. So this is NDVI. Whereas the WDRVI will look like this. So it's even changing at high LI values. So this may be 2, 4, 6, 8. So in rainforest, in general, you will find that the LAI values are very high. They are basically known for their dense canopies. So the LAI values are very high. So LAI values would in general be in excess of 4 and even 6 in rainforest. The tropical rainforest I'm talking about. So that is how we countered the issue of NDVI. There are other solutions to this problem also. Some of them take a sigmoidal tangent to the NDVI rather than using the NDVI directly, and there are several other indices also developed to counter this issue. One such index is the Enhanced Vegetation Index, which is EVI, which also counters the same issue. Okay, so we are done with this with the questions for today's class. But before moving into the exercises, I will like to just explain the common, vegetation spectral reflectance features. So you see that in the visible region, there are two dips to the reflectance curve of a healthy green vegetation. So these two dips happen because of the chlorophyll absorption. Then it suddenly shoots up when we move from the visible region to the near infrared region. The reflectance increases suddenly to around 50% and even 60%, depending on the type of plant or depending on the kind of stress which is being faced by the plant. Okay. And then it dips firstly because of the reflectance due to spongy mesophyll. Mesophyll is a kind of pigment inside the chlorophyll leaves. And then there are when you move into the shortwave infrared region, you see that there are dips at three prominent wavelength ranges: 1.4 microns, 1.9 microns, and 2.7 micron. That is because of the presence of water in the leaves, and that is something known as the water absorption band. So this is the spectral reflectance feature of a healthy green vegetation. And most of the vegetation indices actually exploit this massive difference in the NIR and the red band reflectance to produce new vegetation index. Now, just a brief about the Landsat 4.5 thematic mapper specifications, because the exercises which we are going to, conduct today are going to be from the Landsat 4.5 thematic mapper itself. So it consists of seven different bands. The first three bands are the blue, green, and red bands. Then band four is the near infrared band. Five is the shortwave infrared band, and then moving on into the other band features. The resolutions are more or less same for all the bands, except that of band 6, which is a thermal infrared. uh, the resolution varies from 120 to 130 uh, meters for it. So we will take up some exercise problems just to understand how we use remote sensing for practical applications. Okay, so the first exercise would be to let's let's plot the histogram of some images. Okay, so those images, the images with the seven bands, they are taken from the Landsat thematic mapper TM itself, Landsat TM, from the USGS Earth Explorer website. So let me show what these images are first of all. Yeah, so these are the images which I have taken for this illustration. So this is the band 1 image from thematic mapper again. Band 2, band 3, band 4, band 5, band 6, and band 7. And this is the live the real picture of that region. Okay, so one thing which you can see is that this is definitely a water body, and these darker features should also be some inland water bodies, maybe some lakes or ponds or something like that. Okay, now let us just zoom into it. You can see that it gets pixelated as we are zooming in. So these pixels will have a particular size, the size of which we call as the spatial resolution. The size is 30 meters for this case because it is Landsat TM. Okay, uh, yeah. Any idea what are these brown patches? These brown regions, what might they be? Saket, would you like to answer?
Sir,
Yeah, what are these brown patches in this figure? Any idea?
yes, 12.
Yeah, correct. And what might be these rectangular patches in the figure? They're very rectangular. Any idea? I mean, it's very related to India also.
सर ये सर खेत लग रहे हैं शायद.
You're correct. You're correct. These are croplands. These are agricultural lands, and that is why they are completely rectangular in size. And this thing is basically an urban agglomerate. This is an urban city.
These are.
या जी क्या बोल रहे हो आप फिर से रिपीट करो प्लीज.
सर ये सर मतलब कि कोई गांव का एरिया है जैसे कि शायद लग रहा है ऐसे सर.
हाँ ऐसा ही कुछ
घर
होगा.
घर बने हो ऐसा लग रहा है.
यू आर करेक्ट, यू आर करेक्ट. घर तो नहीं है क्योंकि जो तुम अगर इसको जूम इन करोगे सो दीज आर द पिक्सल साइजेस, एंड पिक्सल्स आर 30 मीटर्स बाय 30 मीटर इन साइज. तो घर प्रोबेबली एक दो पिक्सल में आएंगे. तो वो देखना, डिफरेंशिएट करना बहुत मुश्किल है अगर 30 मीटर का एक तुम सैटेलाइट प्रोडक्ट यूज कर रहे हो तो. लेकिन इट्स वेरी इजी टू डिफरेंशिएट बिटवीन द लैंड फीचर्स लाइक क्रॉपलैंड्स वर्सेस दैट ऑफ द सॉयल फीचर्स वर्सेस दैट ऑफ द अर्बन एरियाज थ्रू अ 30-meter resolution satellite, right?
यस सर.
And this is definitely a water body. This is an inland water body. Then these may be roads. These linear features, they may be roads. If the linear features are irregular, then there may be some rivers. but roads are in general regular in size. So these are definitely roads. Okay, so let's take up the example. So we have images from 7 different bands. Let's plot their histograms as was discussed in the first exercise.
सर इसमें सर इस फिगर अभी जो आपने दिखाया था,
हाँ हाँ हाँ.
सर जो इसमें ओशियन बॉडी है वो सर ब्लू कलर की दिखाई दे रही है वाटर पे, और सर जो इनलैंड वाटर बॉडी है वो सर डार्क कलर में आ रही है सर दोनों वाटर बॉडी।
कॉन्स्टिट्यूएंट्स अलग होते हैं ना इसमें. इनलैंड बॉडी में फ्रेश वाटर ज्यादा रहता है, तो आयनिक कंसंट्रेशन आर वेरी डिफरेंट. करेक्ट. But the funda is that, I mean, the basic funda I'm telling you, the funda is that, I mean, if you are a remote sensing scientist, uh, if you want to delineate water bodies, I mean, if you want to distinguish them from other features, you would just see the reflectance. The reflectance of water bodies is very low when you compare with it with the other usual surface features like soil or vegetation. Okay, so we will do it in the exercise today. So the first one is to let's plot the histogram of some images. So I have already prepared the MATLAB codes, and I will keep explaining each of the step here. So the first exercise is about plotting the histograms. So band 1, band 2, band 3, band 4, these are all given here. Okay, in the image. So B1, IMREAD is the IM read is basically the code as provided by MATLAB. It's a one line code. If you want to store a band or any image, so let's try it out. If you have any question, you can interrupt me in between and ask questions. No issue with that. So B1, as you see, is an 850 by 1100 based array. Okay, so there are these numbers. These numbers are nothing but the DN values, the digital numbers. Okay, so it is basically 850 rows and 1100 columns in size. And this is uint8. Uint8 is that it is unsigned integer and 8-bit. It's an 8-bit image because it's Landsat TM. Landsat TM radiometric resolution is 8-bit. So it is an unsigned, means there are no signs in it. It is, and all the values are integer. The digital numbers are anyways integers only, and it's an 8-bit image. It's as simple as that. Okay. So 8-bit image would mean that there are 2 to the power 8 discretizations, which is equal to 256 discretization. So none of the values here would be lower than 0, and none of the values here would be greater than 255. So this is the array or matrix of the image. Okay. So this is B1. Similarly, we store, we just need to paste the location. So in my computer, it was placed in Abhishek folder, in OneDrive in the desktop, and in another folder known as the NPTEL remote sensing, and the image was named band 2. Okay, and it was a JPG image. So I again read the band 2 like this. I'm pasting it like this. So band 2 also came. It's of the same size again. Okay, let's do the same for all the other bands. So this is the step through which I am just storing the values in my computer in the array. Okay, and all these are unsigned integer 8 itself. Means the DN numbers are not negative, and it is all of them are integers, and they are all 8-bit resolution, radiometric resolution. And then I showed you the true color image that I am storing it as nat or natural. Okay, so I did that. Now the time to plot the images. So let's do that. Let's firstly plot the image for band number 1. Subplot is a command which basically okay, let me show. So this is the total image. If I have subplot 2 comma 2 comma 1, okay, so that would mean that the image has 2 by 2 will have 2 by 2 sub images. So there will be overall 2 by 2, which is equal to 4 sub images in each image, and 1 will be the position of the image you are calling. So this would be image 1. This would be called by subplot 2 comma 2 comma 2. This would be called by subplot 2 comma 2 comma 3, and this would be called by subplot 2 comma 2 comma 4. So this is a 2 row by 2 column image, and the numbers you are writing in the very end. Okay, anyways, so let's move to the question. So subplot 1 comma 2 comma 1, so the total image is going to have one row and two columns, and we are calling the first image. Imshow is a command which plots the image. Okay, so let's do that. Imshow b1. So we are plotting the band 1 image, and we are putting a title as original band 1 image for it. Okay, so let's put the image. The figure would look like this. This is the original band 1 image. Now subplot 2 comma 2 comma 1 comma 2 comma 2 means the second image of that same figure, the second sub image. And IMHist or imhist is basically the command which plots the histograms directly. So let's see that also. Let's do that. We are putting a title histogram of original band 1 image for it. So we are done with the band 1 images. The histogram looks like this. So the pixels DNs will vary from 0 to 255, that we all know. And these are the histograms. So histograms are always made with respect to frequency. Frequency means the number of pixels. So the peak frequency, the peak number of pixel happens around what value? Happens around 110 basically, right? Around 110 exactly. The peak happens at 110, and it basically is very low at very high DN ranges and very low DN ranges. So delete all data for the time being. So this is how we plotted the band 1 image as well as a histogram. Now let's do the same for all the other images also. So I will straight away, I'm just doing the same thing, but for the other images also. Band 2 to band 7. Okay. So this was band number 1. This is band number 2. One thing which you observe is that the histogram features are changing a lot when you go into other bands. This is band number 3. This is band number 4. This is band number 5. This is band number 6. Look, very peculiar shapes. Although the number of pixels are same in all the bands, but the reflectance feature or the DN numbers, DN frequencies, they're changing massively. And this is band number 7. So, this first exercise was just to understand that when we move from one band to other, the pixel features, the DN numbers, they vary consistently and considerably. So, this is band number 1 histogram, band 2, band 3, band 4, 5, 6, and 7. They all are very different from each other. So that is what I wanted to show. Okay. Now what about the natural image, the true color image? The true color image was the one which I showed here. This is the true color image of band 3 to 1. Okay. So let's do the same for the true color image also. So the true color image is colorful. So first of all, we need to change it into grayscale. So for that, RGB to gray is the command in MATLAB, and then we are doing the same thing. Let's try it out. Okay, and this is not going to be IMHIST B7, but this is going to be Nat Gray actually. This I've written wrongly here. Nat Gray. Okay. So this is how the true color image in the grayscale and its histogram would look like. This is how it would look like. Okay. Now, I mean, any image which you see through your computers, they have three different features. So one is the red band, green band, and blue band, and that is why we call them as RGB images. So there are three bands, and then we concatenate them, means we fuse them together, and that is how we see those images as colorful in nature. So the other way to do the same is basically plotting the histograms of red band, green band, and blue band separately. So I have first of all fragmented them from the natural image, and then I'm plotting the histograms of the red, green, and blue band separately. Let's see how they would look like. Yeah. So this is the natural image. This is the blue band histogram. This is the natural image green band histogram, and this is the natural image red band histogram. Okay. Uh, yes. Now another way, MATLAB also gives you a way to concatenate it. So the concatenation happens like cat. Cat is the command here. So within these three bands, you will store band 3, which is red, then band 2, which is green, and band 1, which is blue. Now let's do the same thing and concatenate them. So on the left is the concatenated RGB image, and on the right is the original natural image. So do you see any difference between the two? The major difference which we see is that the soil patches are appearing a bit more red in the concatenated image versus the original image. That may be because the algorithm in MATLAB is a bit different than the algorithm which the Landsat people provide the natural image in. Okay, so that is the only reason why they look a bit different. So we are done with the first exercise. Let's move into the second exercise, the second question for today. The second question would be show the scatter plot of bands 3 versus 4. Okay, let's do that. So in the second example, we will take that up. I need to close all these images firstly. If there is any doubt, please feel free to ask me. You can do the same exercise on Python or R also, by the way. I am doing it on MATLAB because I am more comfortable on MATLAB. So the second exercise is the one in which we are going to plot the scatter plots of bands 3 versus that of band 4. So we are doing the same thing again. I've already explained the codes, code details. These are just one line codes. So I'm storing band 3, then band 4, and then I'm vectorizing the bands actually. So band 3 and band 4, they are actually, okay, let me show it like this. Clear all CLC. Through this we can remove the workspace as well as all the command window. So we are first of all reading band 3 and band 4 DNs, the DN values. So they are basically arrays of size 850 by 1100. Now we need to vectorize it, so which would mean that the array would contain only one column. So we're vectorizing it like this. So the vectorized one has 9,35,000 rows and only one column. Okay, now let's plot the scatter plot between the V3 and B4 vectors. The scatter plot looks like this. So on the y-axis are the band 4 digital numbers, and on the x-axis are the band 3 digital numbers. So are we seeing in relation between the two? Are they even coherent? Any idea about it? Let's take it out. Let's understand. Let's do a basic fitting exercise. Let's fit them linearly. Yeah, so it would be linear, and let's write the r square and the r. So sorry. So we are observing that the r square is very decent. It's around 0.6. So this means that there is a close coherence between the digital numbers of band 3 and bands 4. And let us suppose there is some irregularity in the bands, then usually this coherence will not be as high as this. So we can surely say that there is a coherence between these two bands, and they are for the same, I mean, they are produced from the same region. Okay, so that is the basic inference from this second question. Let's take up another question now. Contrast stretch bands 3 and 4. So there is something known as stretching the contrast. Contrast is basically the easiness of reading the images. Okay, I will explain it through one example. So we are trying to contrast stretch the band 3 and the band 4 images. Let's do it. So that is the third question. We are again reading the band 3 and band 4 DNs like this. And let us firstly plot the image also. So this is the original band 3 image. Okay. Now let's plot its histogram. This histogram we also plotted in the first exercise, by the way. So this would look like this. Now the next part would be the stretching. So if you want to stretch it, so you can see that the histograms are like this. So towards the very low DNs and towards the very high DNs, not many pixels are populated there. They're basically localized towards a particular region. For example, around this 30 to 40 DN mark, most of the DNs pixels are localized. Same localization, dense localization is there in this 80 to 90 mark, probably 70 to 80 mark. Then again, these regions. Okay, so if we want to stretch it, just like I mean, to populate each and every digital number, it would actually result in enhancement of the contrast. So let's see that how that would happen. So that is done using a process known as the histogram equalization. You will read it in the upcoming lectures. Actually, you will read its theory in the upcoming lectures. Uh, so the code for the same is hist eq. So through this we will plot the image as well as the uh, histogram equalized histograms. Let's see how they look like. Look, so after the stretching, the contrast stretching, now the pixels are. Yes, any question? Okay, after we stretch the histograms,
say sir,
yes, please. Yes, please ask me question. Whatever you were going to ask.
सर लाइव सेशन से नहीं सर, अदर क्वेश्चन पूछना था.
Okay, you can ask. You can ask. Why not?
सर जो एनपीटीएल के सर कोर्सेज हैं,
हाँ.
सर जो एनपीटीईएल कोर्सेज हैं ये सर अभी सर जनवरी से जुलाई के सेशन में चल रहे हैं और इसके बाद ओपन है, तो वो वही कोर्सेज सेम कोर्सेज जुलाई से दिसंबर में भी ओपन रहेंगे।
नहीं नहीं नहीं, यूजुअली जुलाई से दिसंबर में अलग कोर्सेज चलते हैं, जनवरी सेशन में अलग कोर्सेज चलते हैं। लास्ट बार मैं टीए था एक कोर्स के लिए जिसका नाम था रिवर इंजीनियरिंग, तो वो कोर्स इस बार
अच्छा।
फ्लोट नहीं हुआ। तो इवन सेमेस्टर में अलग कोर्सेज चलते हैं एंड ऑड, जितना मुझे नॉलेज है, मेरा 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 भी नॉलेज इतना अच्छा नहीं है। मैं आई मीन दिस इज जस्ट द सेकंड सेमेस्टर आई बिकम अ टीए इन इन दिस एनपीटीईएल थिंग। सो मेरा नॉलेज इतना अच्छा नहीं है, लेकिन जितना मुझे पता है ये कोर्सेज रिपीट,
बस सर
या सॉरी,
रिपीट हो भी सकते हैं, मतलब चांसेस हैं इसके भी।
हो भी सकते हैं मुझे, लेकिन जो कोर्स मैंने लास्ट सेमेस्टर में लिया था वो कोर्स इस बार ऑफर नहीं हुआ है, जिसमें मैं टीए था वो इस बार ऑफर नहीं हुआ है। ओके ओके, सो
ओके।
let's see its contrast enhancement. So this is the one for band 3. So you see that many features are now better to be read. I mean, many features can be read in a better way after you, I mean, stress the contrast of the band 3 images. You can read it much better. It was very dark in the original image. Now it is not that dark and it is a bit easier to read. So that is the difference it creates. Let's do the same for band 4 image also. Again, so what does it actually do? So many features here, they were not clearly visible, now they are. Let's zoom into the same point of these two images. You can see that the visibility is much better in a contrast stressed image. So that is why we do it. So most of the pixels were dark. That is why the peak in this image was around a DN number of 30 probably. But now they are much more brighter, and that is why, I mean, you can see that the histogram has changed. The features can be understood in a much better sense in such images. Okay, so we are done with this question also. Let's take up the next example question. The next example would be to produce standard, sorry, produce standard FCC. You know what is FCC? Okay, FCCs are basically false color composites. FCC. Okay, so usually in RGB images, we concatenate them as three bands: red band, green band, and the blue band. Okay, but when you are interested about vegetation, if you are a researcher interested in vegetation, we know very well that the NIR band becomes extremely important. So we can create another RGB image, which is something known as the standard FCC, in which we are concatenating the NIR band, green band, sorry, the red band and the green band. We are omitting the blue band altogether. Okay, so red band will be given a sorry, NIR band will be given a red color, the red band will be given a green color, and the green band would be given a blue color, and that is how we will be preparing the images. So the benefit of this would be that most of the vegetation features, because they have very high reflectance in the NIR values range, they would appear reddish in color, and we will be very easily able to distinguish the vegetated features pixels. So let's take up that exercise. So we are trying to build standardized images. So for that we need band 2, band 3 and band 4. And I'm also showing the natural images. I mean loading the natural images just for a comparison. Clear all. CLC. Let's cancel these images. Okay. Okay, so the first stage is basically concatenating it, but in this time we are not concatenating red, green and blue, but NIR, red and green. Okay, so we are producing it. Let's see how these images would look like. So on your right is the original natural image, and on your left is the standard false color composite or standard FCC image. So whatever greenish features were there in the original image, they appear red now. Okay, and soil features, they now appear green. So it's very easy to distinguish the vegetated features using standard false color composite, and that is how it came into prominence. The water bodies still remain blue in color, by the way, because they have low reflectance. But the vegetated features appear red. So that is one convention. Now you can now I mean in this remote sensing course there is no convention of colors as such. You can use any three band combination, and you can prepare any false color composite image. If you are interested in, let us say, the shortwave infrared image, then you can concatenate shortwave infrared with nearer infrared and green band to produce another set of false color composite image. So it all depends on your requirement in this course. Now let's understand what would be the pixel value. What would be the pixel value for row equal to 15 and column equal to 45? Let's find it out. So row equal to 15 and column equal to 45, DN number, let's extract it. So the DN number is coming to be 21. So row 15, column 45 would be somewhere here. And it is, the DN number is coming to be 21. So any inference out of it? It's a water body and the DN number is very low. Why is it like that? Any idea? It is because the reflectance of water bodies are usually much lower than the other usual surface features, and that is why the DNs will also be very low. So that is the explanation. So the likely feature, even without looking at the image, you can say that the likely feature, if it has just a pixel DN value of 21, it would certainly be water. So it is 21, and it may be water. Let's take up another question for today. Now let's produce NDVI image from this. Okay, so NDVI, you know very well, is basically NIR band minus red band by NIR plus red. So for vegetation, NDVI would be greater than 0, sorry. It's common sense because the NIR reflectance is much larger than the red reflectance. So let's check it out. So in the next exercise, we are actually going to plot the NDVI for the same image. So for that we need band 3, which is the red band, and band 4, which is the near infrared band. And for doing any arithmetic operations on MATLAB, you need to convert an image which was in the unsigned integer 8 format into double format. Okay. So double is a way of storing numbers in floating integers in MATLAB. And this is there even in other coding languages, by the way. So let's convert into double, and then in this line, we are doing this arithmetic operation. We are finding the difference between the NIR minus red band on the numerator, and we are summing up NIR to red in the denominator to find out the NDVI. So let's see that. Let's see how it would look like. Yes. So this is the NDVI. This was the NDVI in grayscale, and this is the NDVI in a color map, in a colorful map. So why? I mean, we human beings, we typically find it very hard to distinguish between two different grayscales. Our eyes are not extremely sensitive to capture small variations in grayscales, but our eyes can definitely capture variations in colors. So this NDVI image would be much more easy for us to understand than the one which we took up earlier. So, any idea what would be the red colored features on? I mean, red colored pixels. Any idea about it? Red is over zero point 0.8 actually. Would you like to comment? This is the NDVI map, and many pixels are reddish in color. Any idea? So, I mean, we already discussed it. When the vegetation, I mean, when the pixel is rich in vegetation, the NDVI is actually greater than 0. And that is why you can see that most of the pixels have actually very high NDVI. And some of them very high NDVI, I mean, till even 1. So, this was the NDVI question. Now, another exercise. Clear all CLC. Let's take up one more problem. We just have 2 more problems left for the day. Okay, so the next one is basically produce band 5 minus band 4 image. Let's do it. It's very simple. It's just a arithmetic operation. It's very straightforward. So we first of all read band 5 and band 4. We then convert them into floating values. That is double is the code to convert them, and then we subtract band 5 to band 4. And then we plot them. Let's see how they would look like. Yes. So band 5 minus band 4, the DN numbers, they would look like this. Okay. And the final question for the day is question number 6. Sorry, 7. We already discussed, I think, yeah, 6 questions we discussed. Question number 7. Approximately estimate the area occupied by water bodies in the image. Okay, so how would we do this? Let me first delete all the other. Yes, so we have these images. How can we understand? I mean, how can we estimate the total area of water bodies in this image? Any idea? Would you like to comment anything? This is the water body, this is again a water body. But how to estimate that the total area of water body in the image? Okay, so we will basically exploit the spectral reflectance feature of water bodies being, I mean, the water body is showing very low reflectance in the visible region. We'll exploit uh, that logic to come to the total area of water bodies from this image. So let's do that. See, okay. So we first move into the band 4. Band 4 is the one which is near infrared, and in band 4 the reflectance of water bodies is almost zero, almost zero. So the band 4 features which have very low DN values would certainly be water bodies. So 24, 27, these should be water bodies. Now let's see, we are let's plot it first of all, the band 4 image first of all. Okay, so this is how the band 4 image looks like. We are just plotting it in a color map. So the lower the DN values, greater would be the probability that it is a water body. So you can see that the water body here, they look bluish in color. All the water bodies here. Okay. So now how to segregate the water bodies from the other land cover types? So for that, we need to set a threshold. So let's suppose we are setting a threshold of 40. So any DN number which is lower than 40 can be set as a water body, and anything above water body 40, DN equal to 40 would be set up as some other land cover class. So let's do that. So we set a threshold and then we plot a figure. So this is the new figure. So any dark feature here is basically a water body, and anything red, there are only two colors. I have only defined two plotted it using two colors. Anything red is not a water body, anything black is a water body. Okay, now how would we find out the total area of water body? So the total area of water body would be very easy to find. We will just calculate the number of pixels which have a DN value of 0. We have actually changed that values, DN values into 0 and 1. So all of them which have DN value of 0 will be water bodies, and all of them which have DN value of 1 will be not water bodies. So let's calculate the total number of pixels which have DN equal to 0. So let's see it. So there are only 224760 pixels left. Okay, so 224760 pixels. So from it we got that the water body pixels, water body pixels were equal to 224760 numbers of pixels. Now how to find the area of the water body? Area of water body is nothing but the number of pixels 224760 into the spectral resolution of each pixel, which is 30 meters to square, because each pixel is a square. So that is how we will find the area of the total water body, and the area comes out to be 202.284 square kilometers. Okay, so original number of pixels were equal to, what were the original number of pixels? The original number of pixels were actually let's check what were the original number of pixels. Ordinal number of pixels were 850 by 1100. Okay, so ordinal number of pixels were 850 by 1100. So percentage of area with water would be the total number of pixels containing water, 224760 into 100 by 850 into 1100, and that comes out to be nearly 24 percentage. So percentage of water, just put this code here. The percentage of water PR, that is around 24%. So almost one fourth of the total land area. I mean the total land area, one fourth of it is water body. Quarter of it is water body basically. So that is what we found out from this example. So we are done for the day. But if you have anything to ask, please feel free to ask me. This was the first such weekly live session in which I took some examples, because I believe that remote sensing is a very practical course. Learning the theory is all right, but uh, if you can use it practically, then you can do several things. So that is why I decided to, I mean, take up some examples to just discuss it. So we are done. I mean, we are done with the contents part for the day. If you have any question, please feel free to ask me. Any question? Saket, any question from your side?